set up in here TV so that I can show you the lecture that I did several weeks ago about the micro injection. So you'll have Cynthia, those two, but I haven't worked that out yet with Pat. So I'll post an email on the website.
It's on YouTube. So, like, worst case scenario, someone's computer could play on a projector.
It is on YouTube?
Yeah.
Because I was just getting stuff from them saying, look it over, and if it's okay, we'll post it. So it's on YouTube.
Most recent one? The standards are so
Yeah.
Anyway, we'll have to get a TV in here. I mean, I could stick a laptop up here.
Well, doesn't this thing work?
Yeah. So that'll work?
Yeah. Presumably, yeah.
And you can hook it into YouTube?
Oh. Well, this is the 20th century, 21st century.
But I'm a 20th century guy.
Me too.
Is there somebody here who knows how to do this? So you know where the lecture is. This is the
Yeah, if you just YouTube, like, Morgan, Oxford, Poincaré lecture.
So you have the link. Does somebody know how to work this thing?
Well, you need a computer, and there's a gizmo over there where you attach your computer.
That complicated.
This thing right here. Well, there's also a
Sometimes the sound.
USB.
Well, Pat, I'm sure. we can-
Yeah, I wrote to Pat, but he hasn't
All right.
changed the response.
Is this next Monday we're talking about?
Yeah,
Oh,
Monday, a week from today. All right, so today I want to talk about, shift gears and talk about a more combinatorial, maybe algebraic approach to homotopy theory, which is the subject in simplicial sets. You didn't bring your chalk.
No.
I'll try this.
Use the one, try the blue box, or is that colored chalk?
That's color chalk. Let me try this. See,
I can get you some.
So,
No, that's bad chalk.
how's that? Is that okay? So this is a category. Its objects are ordered sets. N, which is the ordered set, 0, 1, N. So those are the objects. One for each integer, and one for each non-negative integer. The morphisms. So I should say Hom in this category. Well, N to M are order preserving functions from N to M. And now here, when I say order preserving, I'm using the Bourbaki notion of how inequality should be addressed or denoted. So to Bourbaki, a positive integer is 0, 1, 2, 3, and a strictly positive integer is 1, 2. So the word with the name without an adjective, without the adjective strict, should be the weak inequality. And if you want the strong inequality, you should put strict. Now, of course, nobody does that. Nobody refers to the positive integer as meaning 0, 1, 2, 3. But I'm going to do that for my order preserving maps. So this means weakly order preserving. It means if A is less than or equal to B, then f of A is less than or equal to f of B. And when I want things to be strictly order preserving, I'll say strictly. So, order preserving means weakly. Okay, in this sense. And if I want the strict form, I'll say strictly order preserving. Okay. So the morphisms are the order preserving, i.e. weakly order preserving maps. Okay.
So you can map everything to 0 and that'll be order preserving.
That's right. In fact, that will be allowed in that. Okay, so that's category. A simplicial set is a contravariant functor. From this category I just defined, delta, to the category of sets and set functions. Terms a simplicial set, K, a simplicial set, consists of, well, first of all, sets, K, n, indexed by the positive integers, positive integers. Okay. And set functions V in M from K M to K N for each order preserving map. And the fact that it's contravariant is the direction of the arrows has been reversed. And these maps are subject to the composition
So you don't have a
rules.
notation for the map from N to M. Or because the,
Yeah, well, the alpha, one for each order preserving map, alpha. Maybe that's a better one.
that should be, shouldn't that sort of be K of alpha?
No, the sets, so maybe alpha,
What's the name of the functor?
I haven't given it a name. K is the name of
Right, so then K sub N is a set and K sub alpha is a morphism.
it. Okay. Good. For each order preserving map, alpha, and these have to satisfy the composition rule that's derived contravariantly from the composition rule of these functions. Now, in fact, you don't have to really go to this length to describe all the set functions here. Turns out that any order preserving map from N to M is a composition of a sequence of two elementary type maps. It's a sequence of face maps. Well, the indices are going to bounce all over here. So let me just call it K times 1, 0, K. So this is the map, the strictly order preserving map that misses I. So Fi of R is R if R is less than I, and it's R plus 1 if R is greater than or equal to I. So a picture of this map would be U0 k minus 1. So it skips I minus 1 I. These are successive here, I minus 1 since here, and I maps to I plus 1. Okay. So that's the ith boundary map, I guess. Well, the ith face map. So that's one of them. So you have maps like that, and you have degeneracy maps. That go from n k to k minus 1. That's 0, 1, k, 0, and minus 1. These are order preserving, they have to be. They're surjective. And F invert, degenerate SI. And SI inverse of I is I and I plus 1. So this time you're doubling at a certain place. You have two successive integers that go to the same place. The place they go to is I, and the things that go to I are I and I plus 1. Okay. So that's the ith degeneracy. So you have these face maps and degeneracy maps. And dual to those, that is the image of these maps under the functor, will be dual to Fi, or K of Fi is called boundary map from K in the ith boundary map from K in to K in minus 1. And dual to these are the degeneracies from K minus 1 to K. So I said, and it's very easy to establish, that any order preserving function between two of these sets is some composition of these two elementary functions. So for example, the function that Tony mentioned that sent everything here to 0 is just the composition of a bunch of these degeneracy maps. Just keep degenerating. Now, there are the basic relation. These maps have to satisfy a relationship or relations. So the relations are the first one is boundary I, boundary J, is boundary J minus 1, boundary I, if I is less than J. Okay, I'll talk about this one for a minute, and then I'll just put the others up, and they're very similar relationships. I won't go through the details of the others. But let me talk about this one.
So here, I mean, to be picky, you're using the same SI for the thing and for its image under the phone.
Yeah. Whereas I didn't do boundaries. That's fairly typical, actually. And I have different names over here. I call these face maps and boundary maps, whereas these are called degeneracies and these are called degeneracies. Okay. So this composition will be a map from Kn to Kn minus 2. Both of these. And the easiest way to think about it is to think what they correspond to under the face maps. Because whatever the condition is, whatever the equality is, it's induced from the equality of face maps. But of course, this is a contravariant functor, so you have to be a little careful about the order. But the way to sort of keep that straight is to think about, well, we're going to do the singular functor in just a minute, the singular set, the singular simplicial set. So imagine that Kn is a set of maps from the n-simplex to x. And then boundary I is restriction to the ith face. Okay, so that's a paradigm always to keep in mind, because then you don't have some abstract contravariant functor. You're restricting. Restriction is a contravariant functor, and if you think of it in that language, you won't get confused about what order we put things in. So we're imagining here we have delta n, 0 to n. We have delta n minus 1, 0 to n minus 1. And here we have delta n minus 2, 0 to n minus 2. Okay. Here, we're supposed to restrict to the jth face. So how do we do that? Well, the jth face sits right here, and it'll be the unique integer that's not in the image of this map. So the map will break here and have that kind of image with a hole at j. Okay.
So here we're letting Kn be delta n, and I guess I'm confused about what.
Now Kn here is the set of continuous functions, continuous maps of delta n into x. So just as that's one way to get a contravariant functor. I mean, I'll show you some others too, but just keep this in mind as I do this picture. So this is the jth face, fj, and the image inside delta n is all the integers except j. Now I want to do the same thing over here for the ith face, and I is less than j. I is strictly less than j. So there's an I here, which becomes, so j is here, j minus 1. Now I have I, and so what happens is this thing is embedded here, skipping the ith vertex. And then when you go over here, you miss the ith vertex. So fi compose fj maps delta n minus 2 into delta n. It's strictly order preserving, it's injective, and it misses the vertices, the image misses the vertices I and j. This is provided. I is less than j. And so contravariantly, that's boundary j, boundary I. Okay, would be restriction to this codimension 2 face. All right, now let's do it in the other order. Suppose I first color. Suppose I first do delta I. So I first do face I. So I first do face I. 0 n minus 1 face I. 0 to n. So that will leave out vertex I. Okay. And now I do here face j minus 1. Well, that will leave out the vertex j minus 1. So the image of this map is everything except the vertex j minus 1, and the image of this map is everything except the vertex I. But because I is less than or equal to j minus 1, under this map, j minus 1 goes to j. So this composition also is the embedding of delta n minus 2 and delta n, that this is the same two vertices. And that was under the assumption that j minus 1 was greater than or equal to I, which is the assumption that I is strictly less than j. Any questions about that? I mean, you probably need to think through it for yourself, but it should be clear what the idea is. So I'll now write down the other axiom over here. The other conditions that you have on the boundaries and degeneracies.
So what's the x here?
Sorry, what's what?
What's x?
What's x?
You wrote.
Oh, I just think of x as a topological space.
Continuous maps.
I mean, to have a, I gave this argument for the face maps in the opposite order. So that proves the result for any contravariant functor. But if you want to keep in mind a contravariant functor to help keep the argument straight, think about continuous maps of delta n into x. That would be the nth set. And boundary I would be the restriction of the map to the ith face. Degeneracy I would come from a collapsing of delta n plus 1 to delta n along an I plus 1 direction and then composed. All right, so here are the rules. I just did this one, delta I, delta j, is delta j minus 1, delta I plus j. There's a similar one for the degeneracies. Si, Sj equals Sj plus 1, Si, if I is less than or equal to j. And now there are rules for how to compose boundaries and degeneracies. And you can check all of these in exactly the same way I checked that one. Okay. So to define a simplicial set, you have to give a collection of sets indexed by the non-negative integers, the Kn, and you have to give maps boundary I from Kn to Kn minus 1. And this is from 0 less than or equal I less than or equal n. And you have to give degeneracies from Kn minus 1 to Kn for 0 less than or equal I less than or equal n minus 1. And they have to satisfy these rules. And then for any order preserving map, you take an appropriate composition of these to figure out what the map between the relevant sets would be. So let me now give you the example that I was using to implicitly in what I was just doing.
So these rules all follow just from contravariance or from what?
Yeah, from contravariance applied to the way these elementary order preserving maps compose. So I showed you how two face maps compose. You do it one way, you do it in the other order. There are similar arguments for these degeneracies and then for mixing face maps and degeneracies. And if you look at these relationships, if you have any pair, delta I, delta J, either it's going to any pair delta I, delta J, it'll either be the left-hand side of an appropriate inequality here or a right-hand side. So you know how to switch any pair of delta I, delta J from this equation. Likewise, you know how to switch any pair Si, Sj from this equation. And these are the equations that tell you how degeneracies and boundaries interact. Okay. So, X is a topological space. I'm going to define the simplicial set sing X, the singular simplicial set associated to X. So I have to give you sets and these functions between them. So I can tell you what sing n of X is. That's a set. It's a set of continuous maps from delta n. Let me denote it that way. You'll see why I put the bars on. This is the geometric n simplex into X. Continuous maps of the n simplex, that geometric object, into X. So that's a set. I need boundary maps. Boundary I is supposed to, so if F is an element in sing in X, i.e. F is a continuous map of delta n X, I need to define, I need to tell you what delta I of F is. Well, maybe I should call this phi. And this is simply phi restricted to the ith face. The ith face is what we were talking about before. The inclusion of delta n minus 1 and delta n is a simplicial map. So it's determined by what it does to the vertices. The vertices map in an order-preserving fashion, skipping the vertex I. So that's what delta I is. Si of phi is supposed to be a map from the n plus 1 simplex into X. And what I do there is I take the n plus 1 simplex and I collapse it, degenerate it onto the n simplex. You think of points here as having affine coordinates t naught up to tn plus 1. So these are real numbers. They're greater than or equal to 0, and their sum adds to 1. So ti greater than or equal to 0, summation ti equals 1. Those are the conditions here. You map this is Si. T naught ti plus ti plus 1. So this is the map induced by a simplicial map of the n plus 1 simplex to the n simplex, order preserving on the vertices, 1-to-1, except for the fact that it sends the ith and the I plus first vertex both to the ith vertex. So it doubles the ith vertex and everything else is.
That says ti plus 1?
Yeah. Because both. Remember, this is, what does this refer to in affine space? This is summation ti vi, and vi is the ith vertex. Well, if I'm going to send both vi and vi plus 1 to vi, then the coefficient in front of the new vi will be the sum of the two coefficients. So this is the collapsing map that collapses along parallel to the edge, connecting the I and I plus first vertex.
So what's the picture for like from delta 2 to delta 1?
Here we go. 0, 1, 2. So S, S1, 1. Just the vertical projection, which I haven't drawn it as a standard picture, but that's what it looks like. So the fibers are these things parallel to this edge containing I and I plus 1. If I drew it in the standard way, then the fibers per images of points would look like that. This would go to 0, this would go to 1, and these are the level sets. So this really is the restriction to the face, and this really is the pullback under the degeneracy. So the degeneracy is a map from, well, and it's an easy exercise. It's the same exercise you can do purely combinatorially to prove all of these rules. But suppose I had an order preserving map from an arbitrary order preserving map. And I have a continuous map, so I have an element here, so phi is in sing m of x. This is alpha. I'm supposed to have some alpha star of phi in sing n of x. And what is it? Well, these are the vertices of the n simplex. These are the vertices of the m simplex. This order preserving map gives you a simplicial map from the n simplex to the m simplex, which may collapse stuff, may not hit everything, whatever. Send the vertices where they go and extend affine linearly. So you get some simplicial map from delta n to delta m. And then you just compose phi with that simplicial map. So this is the generalization of restricting to a face. That's composing with the face map, or the degeneracy, which is composing with the degeneracy map. You can compose with any order preserved, well, any simplicial map, but we're only interested in the order preserving simplicial maps. Okay. So that's the simplicial, the singular simplicial set. I don't think I'll write this down, but these are the objects of a category. The objects of this category are functors from some other category to whatever category you have in mind, well, sets in this case. And then the morphisms between them will be natural transformations between the functors. So it's clear what a morphism between simplicial sets is. It's a sequence of set functions, kn to ln, if L is the name of the other one, that are compatible with the boundary and phase, boundary and degeneracy maps. Well, that's what a natural transformation between these functors. That's a simplicial set, and I've given you one example, the singular simplicial set of a topological space. Let me give you another example. Suppose I have a simplicial complex. X is a simplicial complex. And there's a partial order on the vertices. The vertices have a partial order with the property that the vertices of every simplex, each simplex, are totally ordered by this partial order. I mean, I could have just said, you have a simplicial complex and you have a total order on the vertices, but it can be a little more general. Okay, so I have some partial order on the vertices, but if I restrict any simplex, that partial order induces a total order on the vertices of that simplex, every simplex.
Sorry, what's a simplicial complex?
Huh?
What is a simplicial complex?
What is what?
A simplicial complex.
What's a simplicial complex? You have a set of vertices, and you have a subset of the subsets of V. So you have a collection of subsets of V. So this is a collection of subsets of V. Every sigma in S is finite. So only around finite subsets. And if sigma is in S and tau is a subset of sigma, then tau is in S. I should say, I'm going to take out the empty set. So these are non-empty subsets, and if tau not equal to an empty set. So it's a set of vertices and a collection of finite subsets of those vertices called the simplices. And they have to be closed under taking further subset. So for example, if the set of vertices is finite, think of those as vertices of a simplex. So take the Euclidean space with the vertices as a standard basis. And then take the affine simplex in there. So here are the vertices. They're the standard unit basis of this vector space. And now you take the simplex, the convex hull of those vertices. So it would be exactly what I wrote over here. Linear combinations, Ti of the vertices, where the Ti are greater or equal to 0 and add to 1. That makes a simplex. Okay. Now we can look at the subsets that actually occur in S. One possibility is S is all the non-empty subsets, and that would just be the simplex. But S could be smaller. For example, S could be this non-empty subset, this non-empty subset, and the three vertices. So that would be a simplicial complex. Yeah. I'm thinking of this in a geometric manner. So for each abstract, a simplex is one of these subsets. And the vertices of the simplex are the elements that make up the set. Those are the vertices. And then I associate to that subset a geometric simplex, which is spanned by those vertices and made this way. And I piece those geometric simplices together by gluing them along common faces. And that's a simplicial complex. But now
That
I'm
sort
going
of
to give you.
assumes that all these things are actually in some big vector space.
Well, you can do it abstractly. I mean, take,
What does it mean?
well, you start with the disjoint union over S, sigma cross delta to the dimension of sigma. So this is just an index, if you will. And when I just take for each abstract simplex, I take an honest simplex of the dimension equal to 1 minus the number of vertices of my abstract simplex. And then I define an equivalence relation. So I take the simplex has a topology, so this disjoint has a topology. And now I form the quotient space where anytime tau is a subset of sigma, tau cross delta tau is identified with a face, the appropriate face of sigma cross delta sigma. Namely, the face of this simplex spanned by the vertices in tau. So if I had a 2 simplex and a 1 simplex, so here's tau is AB, so tau is AB, and sigma is ABC. So before I take any identifications, I have the 2 simplex associated indexed by sigma and an interval of 1 simplex indexed by tau. But now tau is a subset of sigma, so tau corresponds to a face of sigma, namely this face right here. And so I identify this face of the 2 simplex with tau, with the edge going to tau. And I take the quotient topology. The subset of X is open if and only if its pre-image in every one of these closed simplices is open in that simplex. So you don't have to have an ambient simplex. If it were countable, you could put the simplex in R infinity. It would really fit there and then have a nice subset. But you know, if it's uncountable, it's a little harder to think about. Anyway. I thought you only knew what a simplicial complex was. I was assuming that. All right, so now I'm going to define a simplicial set associated with a simplicial complex. So now I want to define S of X in the simplicial set associated with this simplicial complex. So X is still a simplicial complex here. So what is Sx in? It's all functions from 0 up to n to the vertices of X with the following properties. 1, the image spans the simplex. That is to say, the image of these n plus 1 points is one of the sets in my collection. And 2, the map is order preserving. So 0 to n has its obvious order. This is an ordered simplicial complex. So each the vertices have a partial order, and when I restrict to any simplex in particular, this simplex, I get a total order. So the vertices of this simplex are also ordered, and this map has to be order preserving. So let's do it for the interval and see what we get. So the interval, one simplex. So we have the vertices are 0 and 1. And the sets we're talking about, well, they're the 2 singletons, 0, 1, and 0. Those are the simplices of my interval. There's 3 of them. 0, 1, and 0. All right, so let's try to figure that's x. And the order is the obvious order. Okay, now I want to try to say what Sxn is. So I need a function from 0 up to n to this set. So one possibility is 0 up to n goes to 0. Another possibility is 0 up to n goes to 1. Those are the completely degenerate possibilities. And then we have a collection of possibilities like this, 0 up to I. So, sorry. Yeah, 0 up to I go to 0, and I plus 1 up to n go to 1. And that could be for any I, and these are the two extremal cases. This is when I is equal to minus 1, and this is when I is equal to n plus 1. In terms of maps of delta n, this would be the map of delta n goes to 0 in the interval. This would be the map delta n goes to 1 in the interval. And this would be a map that splits delta n. Let me draw this picture again. If I were to take I equal 1 and n equal 2, this would go to 0, this would go to 1, and this would go to 1. In general, you send a certain first string of the vertices to 0, and then you jump over and send the rest to 1. So that's what this thing would look like. And the boundary maps are restricting to faces, and the degeneracies are.
You can also send 0, 1 to 0 and 2 to 1.
Yeah, 2 goes to 1.
No, it's a different way of, this way 1 and 2 both go to 1. I can't, I don't know if I get your perspective correctly.
Yeah, I'm imagining 0 goes to 0, and 1 and 2 go to 1.
Yeah, we can also send 0 and 1 to 0.
We could.
Yeah, okay.
Right, we could. Also, the map was bad. Okay. Well, that's a special case of a simplicial set that I'm going to call delta n. So delta n is a simplicial set. It's M are order preserving maps from M to N. So M here varies, N is fixed. We're talking about delta N. It's going to be a simplicial set, so it has a whole bunch of sets associated with it. The delta M, the delta N sub M. And they are all the order preserving maps from M to N. All of them. Face and degeneracy relations are just compositions with face, and boundary degeneracy are compositions with face and degeneracy. Precomposed. And that's a simplicial set. That's a special case of the simplicial set associated with any simplicial complex. This is a simplicial set associated with delta n, that simplicial complex. So these are other examples of simplicial sets.
So this was like delta 1.
Yeah, this was delta 1. Okay, so this is a way to go from certain topological spaces to simplicial sets. I'm going to give you a functor in the other direction. It goes from any topological space, goes from any simplicial set to a topological space. And it's called the geometric realization. And it's going to look very similar to what I said when I was talking about how to build a simplicial complex out of simplicities. Okay, so we have a simplicial set K, Kn with boundaries and faces, which I won't. Boundaries and degeneracies, which I won't write down. But they have the boundary I. So that's my simplicial set. I start with the disjoint union over n of Kn cross the geometric n simplex, where Kn has the discrete topology. It's just some spray of points, discrete points. And for each one of those points, you have a copy of the n simplex, the geometric n simplex. And you do this for every n. Okay. Now this is just a spray now of simplices, of actual geometric simplices spread out. And I'm going to piece them together by an equivalence relation. And now there have to be two generating equivalence relations. If y is delta I of x, so here x is in Kn, and y is in Kn minus 1. Then y, which is an element in Kn minus 1, plus delta n minus 1 is glued to the I face of x cross delta n. So you identify this n minus 1 simplex with one of the faces, one of the n minus 1 faces of this simplex, namely the ith one. So we're gluing, we have a face which is a simplex, and we have this simplex, and we're gluing its face with the simplex.
It's the face that it is.
The face that it is, right? Well, in some abstract sense. I mean, this has no geometric meaning. It's delta I are just functions. But yes, you want to think of the face that it is. So that's one thing we do. And the other thing we do is the equivalence relation or the degeneracies. And now if Si of y is equal to x, sorry, if y is Si of x, so x is still in Kn, but now y is in Kn plus 1. Then we collapse y cross delta n plus 1 onto x cross delta n. So originally, before we did any equivalence relations, we had y cross delta n plus 1 was one of our freestanding geometric n plus 1 simplices. It's now going to disappear. It's going to get squashed down onto an n simplex. So it's identified with its image in the n simplex. So it's going to get pushed down onto an n simplex. It's not going to be there anymore. It's completely accounted for by the n simplex.
The fibers of the collapse are like perpendicular to the I face.
Parallel to the I face. Just exactly what I was doing before. If 0, 1, 2. I, S1. Yeah. Then I will collapse parallel to the 1, 2. So remember the doubled edge in the degeneracy is I plus 1. I'm going to collapse all those edges and parallel copies to points.
What happens to y itself?
So y is here. Y is just a point or an index or a name. Tells me which n plus 1 simplex I'm looking at.
When you collapse, what is that? What?
Well, so I'm saying so I have a collapse from the linear map from this simplex collapsed onto this one, and the y goes to x.
Just like that.
Yeah. So this is, the y and the x are telling me which pair of simplices I'm supposed to be considering. And I have one n plus 1 simplex and one n simplex indexed by y and x. And I collapse the n plus 1 simplex indexed by y onto the n simplex indexed by x. Yeah, let me maybe give you this example. So suppose this was our simplicial complex, one I had just a minute ago. Well, no, and there will be other in faces indexed by other x's. They're not affected by this map. I mean, they're not in the image of this map. There'll be other degenerate n plus 1 simplices which get collapsed onto other n simplices, or maybe onto this one too, for all I know. So it's for every pair, x and y, with this kind of relationship, you take the n plus 1 simplex indexed by y and you collapse it in a manner described by I onto the n simplex indexed by x. You do that for every pair of x and y that satisfy the condition. You seem totally nonplussed.
No. I'm just wondering, if this induces identifications on the like on the n simplexes, because
Right.
they have
That's
a
right. That's
common face or something like that.
Yeah, that's. Yeah, so for example, this n simplex and this one are going to now be identified. Okay, so those are the two elementary equivalences, and they generate an equivalence relation. They aren't an equivalence relation. You have to let them generate. And what they're generating is the equivalence relation given by sort of all compositions of these degeneracy and face maps. But the theorem is proportion space, or maybe I should say in proportion space, each non-degenerate, so in the quotient space, if x and kn is non-degenerate, and that means is not in the image of any SI. Things in the image of the degeneracies are called degenerate simplices. But if you have one that's not in the image of any SI, then the interior of X cross delta N embeds in quotient space. And the union of these over all non-degenerate simplices of all degrees, all n, is the geometric realization of K. I should have said the quotient space is the geometric realization. So K is the quotient space of this
With the quotient topology.
It's the quotient space. You glue all these, collapse all these simplices, glue the faces in. All those gluings and everything they imply.
So you're saying the union of all these non-degenerate simplices is homeomorphic to?
No, I just say it's equal to as a set. Because even though I mean, these interiors look, you think of them as, you call them open simplices, they are not open subsets of K. And the closure of one of them will include others. So let's just think of let's think of the simplicial set delta 1. See what the geometric realization gives us. So delta 1, remember, it's all order, so delta 1 sub n is all order preserving maps from n to 0, 1. Let's find the non-degenerate ones. So, anybody tell me a non-degenerate map?
The identity on 1?
Okay, so, well, can't have the identity on 1. I'm supposed to send 0 up to n to 0, 1.
Yeah, so like 1 underline. So
1 underline to 0, 1 onto the identity. Right. That's a good one. Are there any others?
0 to 0.
0 to 0. Any others?
0 to 1.
0 to 1. That's it. Every other map is degenerate. Every other map will have to collapse 2 successive indices, one after the other. And that means it's degenerate.
So the picture of the degenerate simplex is something that's technically an n simplex, but looks like an n-1 simplex. As in that picture.
Yeah.
Okay.
I mean, it could be even much lower.
Right.
Right.
So then you make the appropriate outbreak identifications here to.
Right. So it's, you have I and I plus 1 go to the same place. For some i's, you go through I and I plus 1 go to the same place. So it's non-injective. And if you have a non-injective map, then something that lowers degree, you can see easily, because it has to be order preserving, there has to be some I in there so that I and I plus 1 have the same image. So those are the general. So under our decomposition here, we have 3 open simplices. We have this gives us a 1 simplex, so it's this cross I. This gives us a 0 simplex, and this gives us a 0 simplex. So the non-degenerate stuff is 3 non-degenerate simplices, a 0 simplex, open 0 simplex, an open 0 simplex, and an open 1 simplex. and we glued them together so that the topology is the topology together. So the geometric realization of the simplicial set associated with the with the one simplex really is the one simplex. And exactly the same argument shows that the geometric realization of delta n is what I've been calling delta n. So my notation is consistent. This is what I was calling the actual simplex, an affine simplex in n space, and I've introduced this notation for geometric realization. It's all consistent. The geometric realization of the simplicial set that I call the n simplex is the actual simplex, and it's non-degenerate. The simplices are the various subsimplices. Injected maps on the subsimplices. Okay. Right. You just say one more thing about geometric realization. And that is, we have the topological category, and we have the simplicial set category. And we have functors in both directions. In this direction, we have the singular functor associated to a topological space, the simplicial singular complex, or the simplicial singular set. And we have one back here called geometric realization. These are adjoint functors. The Hom in the simplicial set category from K to the singular complex of X. That's one thing you could do. If you have a simplicial set, you could take its Hom in the category of simplicial sets into sing of the topological space. The other thing you could do is you could take Hom in the topological category of the geometric realization of K to X. And these are canonically identified.
Are they inverse?
No, they're adjoint.
They're just adjoint.
I mean, they lie in different categories.
No, I mean, but if you compose this way, is that actually equivalent to
No, can't go the other way. It's only adjoint in this direction. I mean, these are equal, but it's one. I never know which is left and which is right. But one's the left adjoint of the other, and the other is the right adjoint of the first. But they're not adjoint in the other order.
What does it say? Hom sing on the left?
What's the subscript on simplicial set?
That's simplicial sets.
SS?
Yeah. And this is topological. Well, let's think about that. So let's take the geometric realization of sing X. I claim there's a natural topological continuous map to X. So what do I have to do? Let's start with before we do the quotient space, we have these n simplices, where this is a continuous map of the n simplex to X, and here's the n simplex. And somehow I got to get that matched to X. Well, it's pretty clear what I do, right? This is a map of the n simplex to X. Here's the n simplex, map it to X. Right? So sigma comma t maps to sigma of I have a point in this is a continuous map of the simplex to X, and here's the simplex. So you just map this to X.
It's not homomorphism.
Homomorphism. Well, I'm a long way from. I've defined it on one simplex in the disjoint union. So now I have it over all n greater than or equal to 0, k n cross delta n. Just do this on each piece. So this maps to X. Okay. Now I need to check that it's compatible with the equivalence relation. So I have to check two things. If tau is a face of sigma, that when I glue the the simplex for tau to the tau face of sigma, the maps are compatible. But that's obvious. And likewise for the degeneracies. So this does preserve the equivalence relations. And therefore you get a map on the quotient space. Is this a homeomorphism? No. This thing is a cell complex. Suppose X is, the famous, this thing, connected, non-locally path-connected space. This isn't a cell complex. There's no way it's going to be homeomorphism.
What if X is a cell complex?
Even then, this is much bigger.
Is it homotopy equivalent?
That's the point. If X is a CW complex, this is a homotopy equivalence. If X is an arbitrary topological space, it's a weak homotopy equivalence. But it is a CW complex. It's a cell complex. Now, I mean, think about it. You have any topological space, there are uncountably many maps of the n simplex in. That's the spaces of form. Just the intervals, uncountably many maps of the n simplex to the interval. Most of them aren't degenerate. Factor through lower simplices. So this is a huge, huge cell complex. I don't know what you're talking about. If you had a simplicial complex, and if you didn't take all singular maps, but you only took these order-preserving simplicial maps, then you'd get back what you started with. So that's a here. Maybe let's take that there. So that doesn't use sing, it uses.
What is the homomorphism between two simplicial sets?
Say again? What is?
The homomorphism between two simplicial sets. Natural definition.
So it's, I didn't say what it is, but for each n, it's a set function from, in this case, kn to sing n. Yes. And it has to commute with the boundary and degeneracy maps. Commutes with all the structure written down. So, sing x is huge. Huge. Uncountable, normally uncountable number of cells. But if we have an ordered simplicial complex, so by that I mean a simplicial complex and a partial order on the vertices, which is a total order on the vertices of every simplex. Then what I call the S of X is simplicially isomorphic. Sorry, geometric realization of S of X is simplicially isomorphic. So for each geometric simplex in X, you have exactly one non-degenerate simplex that hits it. And that accounts for all the non-degenerate simplices. So there's one non-degenerate simplex here for each simplex of X. And then you have to check it all. It's all consistent. So if you're willing, if you have some extra structure and you're willing to restrict the kind of continuous maps you look at, then you, in this case, at least, you get back where you started. Well, I didn't quite prove that these were adjoint functors, but you see now, if you have a map from K to sing X, you get a map from the geometric realization of K to the geometric realization of sing X, and then on to X. So that's this map. On the other hand, if you have a map from the geometric realization of K to X, for each non-degenerate simplex in K, you have continuous map of delta n into X. And that's enough to send the non-degenerate elements of K to elements in Sing, and then you use the degeneracies to see where everything else goes. So that's right.
What's the relation between SX and Sing of X?
This is a version of, Sing is all continuous maps, and these are, if you will, simplicial maps. And the 0 to n has to go to the vertices of a simplex in an order-preserving fashion. And then if you wanted to think geometrically, you have a different map.
So it's a subset.
Yes. Okay, I thought I was going to have lots of time. Let me show you products in the simplicial category, because they're weird. When I first saw a product, I thought, no way this can be right. But it looks really beautiful the way it works, so I'm going to show you that. So, K in L are simplicial sets. We define the product, K cross L. Well, I need a collection of sets, right? And some boundary and degeneracy maps. Well, K cross L n is simply K n cross L n, which seems completely weird. If you take a product of an n simplex and an m simplex, you're supposed to get something of dimension n plus n. Here we're taking what looks like a product of two n simplices and ending up with another n simplex. And boundary I is simply boundary I of K L is simply boundary I K, boundary I L, and SI of K L is simply SI K, SI L. What could be more trivial? But how can it possibly be right? How can it correspond to anything we're used to in topology? Well, let me show you a simple example. Let's take delta 1 cross delta 1. Yeah, so we'd like to get something like this, right? Well, let's think about its zero simplicities. Well, it has 4 of them, right? It has 0, 0, 0, 1, 0. It's the product of delta 1, 0 with delta 1, 0. Those pairs of zeros and ones. And that looks pretty good. We're hoping to get the square. At least we've got the 4 points. 4 vertices. 0, 0, 1, 0, 1. That's what we've found so far. Now what about 1 simplices? Delta 1 cross delta 1, 1. So how many 1 simplices are there?
1.
Wrong. 4. Wrong. But closer.
9.
9. How many 1 simplices are there here? 3. How many 1 simplices are there here? 3. What?
0, 1.
All right, so let's list them and try to draw them there.
Maybe degenerate.
So we have, let's see, 0, 0. I don't know. I have 0, 1 goes to 0. Cross 0, 1 goes to 0. Where should that be in the picture?
0, 0.
It's a degenerate simplex sitting right here. We have 0, and then we have, so we have 4 like this.
Yay.
The 4 degenerate things degenerate in both factors. Okay. Now we have things that are degenerate in one factor, but not in the other. How many of those do we have? 4. 4. And they are 1, 2, 3, 4. So this one, for example, would be 0, 1 goes to 0, 1. The isomorphism cross 0, 1 goes to 0. Degenerate in the second factor. If you project this onto the second factor, it's degenerate. It goes to 0. If you project it on the first factor, it's non-degenerate. Okay. So we have 4 of those. They make up the edges of the square. What's left? And where will it go? Diagonal. We have non-degenerate cross non-degenerate, which if God is in his heaven will be the diagonal map. And indeed, its boundary is 0, 0 and 1, 1. Okay?
Wait, so there's only one non-degenerate, one simplex, right?
No, there are 5 non-degenerate one simplices. There are 4 degenerate. There were 9 one simplices in all. 4 of them were degenerate.
4 of them were not degenerate cross degenerate, and the other 4 were degenerate cross non-degenerate.
But what does it mean to be degenerate? Remember, it has to be in the image of an SI. That means both factors have to be in the image of the same SI.
Oh, yeah.
Something wrong with that, but anyway. Yeah, these are the 4 degenerate ones. And these edges, they're not degenerate. They're not SI. Okay, and then the 9th one is the diagonal. Well, are we finished? Are there any other non-degenerate simplices? 2 simplices. Well, how many non-degenerate 2 simplices are there?
What? For what? For this one?
Yeah, for yes.
16.
Non-degenerate 2 simplexes.
There should just be one.
There should just be 1. Anybody else want to venture a guess?
There's 2 in this.
There you go. There got to be 2. 1 here and 1 here. So magically, what's going to happen, just to look ahead for a second, is this very crazy product is producing a triangulation of the product. So if you start with 2 simplicial complexes and you take their product as simplicial complexes, you don't get a simplicial complex, right? You get a cell complex where the cells are products of simplices. But if you turn those simplicial complexes into simplicial sets, you still have the same collection of non-degenerate stuff, but now you've got degenerate stuff. And you take the product with itself and you work in the degenerate stuff, you get more simplices and you get a triangulation of the product. That's what's happening. So let's find the non-degenerate 2 simplices. So 0, 1, 2. Of course, it can't be non-degenerate in either factor. And if either factor went to a vertex, then this 2 simplex would have image along one of these edges. So the non-degenerate 2 simplices have to project onto non-degenerate 1 simplices in each factor. So 0, 1, 2 could go to 0, 1. So 0, 1, 2 is supposed to go into pairs, right? So it goes to 0, 0, 0, 1, 1, 1. That would be one possibility. And what does that look like? So 0 goes here, 1 goes here, and 2 goes there. So this will be upper simplex. Or I can take 0, 1, 2, goes to 0, 0, 1, 0, 1, 1. So 0 goes here, 1 goes here, 2 goes there. That's this one. So those are the non-degenerate simplices, and I'll let you work out that there aren't degenerates. So we get this great triangulation of the square. Now, how did I know that I was going to use this triangulation instead of this one?
You want some order position?
That's where the order comes in, exactly. So this would not work for two unordered complexes. I need the ordering. And in fact, if you think about what happens for, I'll let this as an exercise for you, but if you look at delta n cross delta 1, so we have some prism. There's a fairly standard triangulation of this that you've probably seen when you prove the homotopy axiom for singular homology. And the n plus 1 simplices, so in this case the 3 simplices, arise by starting at 0 on the bottom, going along for a while, and then at some point deciding to go from the bottom to the top and continue. In this case, you'll have 3, I guess, 3 simplices in here. You could do that for an n simplex cross 1. N plus 1 simplices, or you go along the vertices for a while on the bottom, and then you jump up to the top and finish in order. That's exactly what this product in the simplicial world will give you. Gives you exactly that triangulation. And is a nice generalization of this concept. Where you start on the vertices here, and the 0th vertex here, you do that for a while, and then you jump to the first vertex, and you do that for a while, then you jump to the second vertex. So it's a nice triangulation, canonical triangulation of this product.
So in general, I can take the non-degenerate maps to be the ones that I can actually draw.
Yes.
Those are the ones that should be.
That's right.
Well, okay.
Right.
The degenerate ones are just like point maps or.
Well, maps that have, as you said, a lower dimensional image.
Okay. And all of this is just to sort of get like a canonical triangulation of the acyclic carrier or something.
Well, it does do that. Turns out you can do all of homotopy theory in this world. Though I didn't get to that. If you look at what I wrote up, I'll put it up on the web. That's do the basics of homotopy theory. I define the homotopy and homology groups. Talk about homotopies of maps. You can do all of algebraic topology, and some things work out much, much nicer, like the product in this world.
So is there a theorem that says that if K and L is simplicial sets, then K cross L is a simplicial, in this sense, is a simplicial set whose geometric realization is what you expect, that is the topological product?
Yes, yes. And it has some sort of, I haven't said exactly what kind of structure the geometric realization has. It's not in general the simplicial complex, because these faces could be collapsed down. but it is a union of open simplices, and the boundary of an open simplex is some union of lower dimensional simplices. So it's close to being a simplicial complex, but it's not quite.
It's not a simple.
But anyway, the simplicial set, the product of two simplicial sets has that. When you take the geometric realization, it has that structure, and topologically, it's homeomorphic to the product of the geometric realizations. It's nice enough so that if you take the geometric realization of the simplicial set and you subdivide it twice, this is a simplicial complex. So the sort of things that can happen to you is you could have a one simplex whose faces, the zeroth and one face are the same. I mean, the zero face and the one face are just maps between sets, so no reason the zero face and the one face can't agree. If I subdivide this once, I put it in the very center, which sits out there. It's still not a simplicial complex, but it is a union of simplices now. But simplices don't meet along a single face. They may meet, as we see here, this simplex and this one have their boundary. But if you subdivide once more, you get a simplicial complex. So it's pretty close to being a simplicial complex, but not quite. You can do a lot of what you do for simplicial complexes you can do for these geometric realizations of simplicial sets. They're close. As I say, I'll try to work out something with Pat or somebody so that you can see me in absentia next week if you want to hear about the plan. And it was a public talk, so it'll be easy. Hardly any very few questions. But I'll put a note up on that. I'll send an email to all of you about the final resolution.
What about afterwards?
I'll be back.
And then what do you do?
Well, I'm going to talk about manifolds next. Fundamental classes, gap products, microduality, linking bearings, and then I'm going to do some rational homotopy.
So what is the point of all of this simplicial sets? I mean, what do we get more than we had to start with this simplicial complex?
Well, the reason that I decided to do them was back when I thought I was going to have more time, I was going to show you Quillen's version of rational homotopy theory. And it's based on simplicial groups. So if you take the loop space of a space, that's a simplicial group. I mean, that can be made into a simplicial group, and then using that structure, Quillen got to algebraic things, which gave you the rational homotopy. That's a very powerful way to think about homotopy theory. That's why I decided to use it. But everybody should know that it exists. Actually, these days, and I should have said this, I was talking about simplicial sets. You can do simplicial things. Anytime you have a category, you can talk about simplicial, the simplicial category of that category. So you can have simplicial rings, simplicial Lie algebras, simplicial manifolds, simplicial Lie groups, simplicial Hopf algebras. So, and in this sort of abstract world that we now live in, between the algebraic geometers and the symplectic geometers, a lot of it is formulated in terms of simplicial algebraic algebra. Right.